anionic part. This is as usual in case of inorganic compounds also, right? Sodium chloride, sodium hydroxide. As such, first we will write cationic part, then anionic part. So here also we will do the same. So first, cationic part, positively charged species. Followed by anionic part. Yes, sir. Yes, sir. Next. Second step. We will not write counter ion. Number of counter ions we will not write. Only we will give the name of counter ion, but not number of counter ion. Right? For example, if I take K4 FeCN6, if I write K4 FeCN6, this is the complex. Now, which is cationic part in it? Potassium. Anionic part. So this I can write as -4. 4 potassiums, balance 4 negative charges. Right? Response, sir. So first we will write point is counter ion. Do not consider number of counter ions. Right. So we will not bother about number of species and so on. For example, I am taking two complexes. For example, I am taking two complexes in this way. Platinum. Yes, sir. CN6, 2 minus is there. Right? To balance that, I want to take one more charge, or I will write, instead of this, I will write cobalt. Cobalt 3 minus is there. Here cobalt is in plus 3. Now I'm writing SO4. SO4 2 minus is there. So I cannot write SO4 2 minus now. So I need to take cationic part, right? So I am taking iridium or rhenium or osmium. Osmium is 8 plus. 8 plus is there means I will write 2 plus. Right? 2 plus. To balance 2 plus, 2 minus is sufficient. So I am taking one more. Instead of osmium, I will take one more iridium, which is in 7 plus, or manganese in 7 plus state. Then it will be 1 plus. Now how I will balance these two charges? Here I will write 2, here I will write 1. Correct? Correct or not? Then also I will not mention it as twice. Right? I will simply name it as 6 means hexa, cyanido, manganese, sulfate. You will not mention twice. So to balance a charge or counter ions, we will not consider number of charges or number of counter ions in order to balance them. We will not consider. Any questions regarding that? Response, sir. Next, while I am writing coordination sphere, while I am giving name for coordination sphere, always I need to name ligands first. Name of ligands first, followed by central metal, followed by central metal. While you are naming ligands, if it is cationic ligands, already we have seen name of the ligand should end with IUM. Anionic ligands, IDO, or terminal E is replaced by O. Already we have seen while we are seeing the nomenclature of ligands. If it is neutral ligands, we will name them as it is. For example, if it is water, aqua, ammonia, double M, amine, right? As such, already we have seen that nomenclature of ligands earlier, right? Now, numerical prefixes. If there are 2 ligands, 3 ligands, 4 ligands, as such, we will give corresponding numerical prefixes. Here we call it as hexacyanide. So, numerical prefixes such as di, tri, tetra, etc. are used.
Sir,
Yes, sir.
instead of di, we can use bi also, sir.
Instead of
Di, we can use bi, sir. Bi.
we can use by, but listen, condition. If a ligand is already having numerical prefix in it, in the name of ligand, already numerical prefix is there. For example, what is this? Ethylene diamine. That name of ligand itself is having numerical prefix, right? In such cases, we have to use naming like bis, bis, tris, tris, and so on, tetrakis, and so on. Is it clear? If a ligands already with numerical prefixes, in its name, in such case, should be prefixed with or should be named with numerical prefixes such as bis, tris, tetrakis, and so on. Is it clear? Only don't use bi, right? We use generally di, right? In case of certain ligands like biphenyl, name of the ligand itself is biphenyl. For example, if the ligand is this, name of this ligand itself is biphenyl. In such case, no issue, right? Common name of the ligand itself, biphenyl, right? In such cases, no issue. Normally, if you are writing any numbers in case of complexes, we have to use di. Any questions, sir, further? Respond.
No, sir.
Next. While you are naming ligands, we need to follow alphabetical order. Follow alphabetical order. While naming ligand, and this alphabetical order is also followed while you are writing name to formula. While you are writing name of the complex to formula. While you are writing formula also, you need to follow alphabetical order, right? For example, ligands are like this. I'm taking one complex, name of the complex in this way. I will take one complex. Platinum, fluoro, chloro, bromo, iodo, hydroxo, nitrito. 1, 2, 3, 4, 5, 6. 6 ligands complex is there, right? What is the name of this complex? This is bromo. B comes first, correct? Then chloro, then fluoro, Iodo, hydroxo. Iodo. Hydroxido. Nitrito. Right? In case of nitrito, we need to mention whether it is nitrito N or nitrito O. Right? Correct or not? Now, while you are giving name of this compound, what you will write?
Sir, OH will be 4, sir.
Bromido. Yes, sir. Hydroxido.
OH.
Yes. Okay, man. This comes first. After this, you will get. Okay, leave it. Huh? Now, bromido, chlorido, fluorido, hydroxido, irido, nitrito, platinum complex. Right? If they give name of the complex, we need to write the formula. Na? While you are writing formula, observe this case. Here also, I need to follow alphabetical order. Which has to be written first? Not alphabetical order based upon the name. Alphabetical order based upon the symbol, formula of the compound. So I have to write as platinum, then bromo, chloro, fluoro, hydroxido, iodo, nitrito. Okay. First, what do we have to write? IR, then N, nitrito. Then I have to write OH. Is it clear? Understood or not? Don't write, while you are writing name, follow alphabetical order for the name of the ligand. While you are writing formula, follow alphabetical order for the symbol. Is it clear? So follow alphabetical order while naming the ligand. Similarly, while writing formula, follow alphabetical order. Follow alphabetical order for symbol. Yes, sir. Any questions, sir? You have any questions in this? Say something. Any questions in this? Online?
No, sir.
No, sir.
Yes, sir. Now see this. Give the name of this complex, sir. Which has to be named first? Potassium, then ligands, and then metal. Correct? If coordination sphere is negatively charged, if coordination sphere is negatively charged, if a coordination sphere is negatively charged, anion, then name of the central metal should end with 8. Right? So what I have to call it as? Ferrate. Right? So name of central metal should end with or should have a suffix ATE as a suffix. Is it clear, sir? Any questions in this? Respond. Do you have any questions in it? Now, give the name of this complex now. Potassium. We don't bother about counter ions, number of species, right? Hexa, cyanido, ferrate. Now, oxidation state of the central atom must be written in parentheses with in Roman letters, right? So shall I write that point? Oxidation number of central atom. Is mentioned in Roman numericals, huh? What we call it as? Will you understand, sir? I am not writing another Roman numericals in brackets. I am not writing. Okay. Is mentioned as. Will you understand, right? In parenthesis, we have to write Roman numerical. Any questions up to here? Response, sir. So I am taking few examples. Observe this complex. Give the name of this complex. Ni Cl2 P PH3 twice. Give the name of this complex, sir. Give the name of this one. Give the name of it. Dichlorido. Or C should come first, now. This is triphenyl phosphine. Triphenyl phosphine. So I have to write it as bis.
Bis, sir.
So dichlorido. Bis. Triphenyl phosphine. Yes, sir. Triphenyl phosphine. Nickelate, nickel. Nickel. It is not anionic. So nickel in brackets oxidation number. Triphenyl phosphine is neutral. Chlorine is -1. So nickel must be
+2.
Right? No need to mention like when you are separating two numericals. I need to use hyphen, parenthesis. There is no space. First letter must be capital. All these rules are as usual for organic compounds also. So no need to mention them. Clear? Or if you want, I will write. It goes on. Okay, well, first letter must be capital. No spaces while you are naming it. While you are writing two numerical prefixes at the same place, right? We need to separate them with hyphen, and that ligand should be named in brackets, parentheses. Clear? Any questions are in this further? Next, I am taking one more complex. NiCO 4 times. One more thing. While you are writing formula of complex also, observe here what I am writing. For few ligands, I am using parentheses. For few ligands, I am not using it. If it is a monoatomic, if that ligand is monoatomic, no need to write any parentheses. If it is diatomic, like carbon monoxide, then I need to show in parentheses. I need to mention that in parentheses, showing that both combined, it is one ligand. Here also, phosphorus, 3 phenyls, all put together, it is one ligand. Understood or not? So in such cases, I will use parentheses while you are writing formula also. Clear? Give the name of this complex, sir. Tetra.
So tetracarbonyl nickel 0.
Correct. Tetracarbonyl nickel 0. Next. platinum, NH3 4 times, again platinum, Cl 4 times. This is +2, this is -2. Here also I have written cationic part first, followed by anionic part. Why I am writing formula also. Give the name of it. First we need to name cationic part. But cationic part itself is a complex coordination sphere. Then I have to name ligands. So ligands first. Name of that. Tetra amine, double M. Correct? Response, sir. Tetra amine neutral. Don't write amino. The moment you write O, it should be anion. Right? So tetra amine, platinum, 2, cationic part is over. Now anionic part. Tetra chlorido. Now I have to write platinate 2. Any questions? Any questions in this? Tetra amine, platinum 2. Here also, oxidation number of platinum is +2. So tetra chlorido, platinate 2. Respond. Any question do you have? Next one, sir. If you are writing name of any bridged ligands, in case of bridged ligands, use mu symbol while you are writing the name of the ligand. Along with name of ligand. For example, iron H2O 4 times, bridge ligand OH, again OH. Is it bridge ligand or not? Right? Both ligands are present between two metal atoms. Give the name of this complex. No, here it is 4 minus. Sorry, SO4, 4 minus, no? 2 minus, 2 minus. Means total charge of cation is +4. Sulfate I am writing 2 minus. Will you understand now? While I am writing 2 minus twice. Now in this, OH is -1. This OH also -1. Then what about both irons? This iron is +3. This is also +3, correct? Water is neutral, no? Right? So both irons put together +6. 2 OH minus ions. Total left is +4. Correct? Water charge is neutral molecule. So because of water molecules, charge developed is 0. Response, sir. Any questions in it? No. See, I need to make a charge of +4, right? I don't know water. We know that water's oxidation number is 0 because neutral molecules. So how many such neutral molecules? 8. So 8 into 0. 2 irons are there. I don't know their oxidation number, X. Plus another 2 ligands are there, OH, each having charge of -2, equal to overall charge +4. Correct? Huh? Over. Correct, sir? Next, sir. Now give the name of this complex. Give the name of it. First, I need to start from one end. Tetra aqua, iron 3. Then iron 3. After that,
Mu.
mu. All right, two hydroxidos are there, but both are bridged, right? So di mu hydroxido. Again, iron or tetra aqua? Tetra aqua, not ferrate. The total complex is positive. Again, iron, again 3. Correct? Then sulfate. Is it clear, sir? Any questions in this? Respond. Tetra aqua, iron 3, di mu hydroxido, again tetra aqua, iron 3, sulfate. Clear? Give the name of this complex. Give the name of this complex. What is the oxidation number of nickel here? Oxidation number of nickel, sir. Overall coordination sphere charges -2. Potassium +1. Correct? Potassium +1. Overall coordination sphere charge is -2. So I have to name nickelate at the end. Now it is EDTA, ethylene, diamine, tetraacetato. Ethylene, diamine, tetraacetato. So what is the charge of ligand? 4-. Means what is the charge of central metal? What is the charge of central metal? +2. Give the name. Give the name of this complex now. Potassium. Or a cationic part. So potassium. After potassium. Potassium. Now, while you are naming name of the complex, what I have to do first? Ligand. Name of the ligand. Ethylene diamine tetraacetato. Correct, sir? Acetato. Tetraacetato, nickelate 2. Any questions, sir? Done? Now I am taking one more. Hepticity, sir. We call it as hepticity. Ligands with hepticity. Just a moment. Ligands with hepticity means hepticity possessing ligands means pi electron donors. If a ligand is donating pi electron cloud, we call it as hepticity. Right? That's what they are saying. How a ligand is bonded to a metal center through a series of continuous atoms. Series of continuous atoms means, for example, if I take ethene, CH2 double bond CH2. So 2 atoms are donating, both are donating lone pair of electrons, that pi bond electrons at the same time. Right? So series of 2 atoms are donating electron cloud at the same time. That's why it is called series of atoms. Then we use this symbol eta for hepticity. Is it clear? So complexes with a series of pi electron donors. We call such complexes or such donor atoms. They may be either aromatic or conjugated. Generally, they are either aromatic or conjugated species. Aromatic or conjugated. In such cases, we use hepticity. Right? Symbol for hepticity is eta. Right? Whereas here I have to use the number. For example, if I write 2 represents 2 series of atoms. If I write 5 here, this X represents number of atoms in series. For example, see the name of this complex. We call it as Jesus salt, I think. Yeah, okay. Jesus salt. This complex. Pi bond is there. It is a pi bond donor. Right? Ethene is there. Ethene is donating pi electron cloud to platinum. Right? So I'm writing it. A.
Sir, can
Platinum.
you keep that image, sir?
That also I will write. That also I will write. Cl3. Now I have to show the ligand. So I am showing the ligand. Eta 2 C2H4. Will you understand? Eta 2 C2H4. This is the complex. Right? It is a square planar complex. It is a square planar complex having platinum as central atom, 3 chlorine donors, and here CH2 double bond CH2. Both carbons has to donate lone pair of electrons. In fact, I have to show that as CH2 CH2 like this. Correct? Towards platinum. I have to show that in this way. In reality, reason? Pi electron belongs to both carbons, na? Every carbon have one unpaid electron in its p orbital. So both carbons are donating its unpaid electrons. Both put together, one lone pair of electrons is donated to platinum. So for that, I am using the symbol eta 2. Are you able to understand the meaning of that eta 2 now? Respond. Any questions, sir? Right? Say something. Any questions in this? And give the naming of this complex then. IUPAC name of this complex. Ethene, simple name. There is no other complexity in it. While you are writing formula only, we use this symbol, eta 5. Right? Simply we write ethene. So trichloridoethene. Right? Response, sir. Any questions in it? Right? Jesus salt IUPAC name. Observe the name. Trichloridoethene. We should not use chloro. Chloro is old nomenclature. We have to write chlorido. So trichlorido ethene. That's all. Right? Platinated to that hydrate they have given another water molecule at the end. Dot H2O. That's why they are writing that hydrate at the end. Right? But we will also use the same. So I am writing dot H2O. Give the name of it. Potassium. Potassium. Trichlorido. Ethene. Then platinate. Oxidation number. Here it is +1 means overall charge -1. Means platinum must be in 2. Correct? Is it +2 or not? +2 hydrate. Okay, ma? Another complex, sir. I am giving one more complex. Fe eta 5 C5 H5 twice. Common name of this complex is ferrocene. Common name of this complex is ferrocene. Right? Now, what is the oxidation number of iron here? Right, C5H5. All carbons are donating pi electron cloud. So how it should be? Is it 5 carbons? Pi bond, pi bond. Now what about this carbon? That doesn't have pi electron cloud. How I can make it as pi electron donor? If I take negative charge, then what happens? Aromatic or not? Right? Don't take positive charge. If I take positive charge, what happens? Anti-aromatic compound, highly unstable. Correct? Such ligands doesn't exist. That's why I will not take positive charge. I am taking negative charge. Now it is aromatic. Delocalization is possible. So can I write, by removing this negative charge, can I write negative charge here and a ring here? What is it? Name of this one. Cyclopentadienyl anion. Correct? Response, sir. So I am taking 2 such dienyl anions. I am taking 2 such dienyl anions. And iron, Fe+2. Fe+2 is sandwiched between both rings. Now, how many carbons are donating electron cloud to iron? How many carbons are donating lone pairs to iron? 10. Right? Actually, I have to draw dotted lines from every carbon. Right? Is it aromatic or not? Aromatic species. Correct? Give the name of this complex. Give the name of this complex. Bis. Correct? So bis, name. Bis. Can write eta 5. Actually, no need to mention eta 5. Right? For your understanding, I am writing it. Eta 5. Cyclopentadienyl. Right? So generally, what for negatively charged ligands, what I am using? O. If a terminal is E, then only I will repeat with O. The name of this complex is cyclopentadienyl, na? Where is terminal E? There is no terminal E. That's why I will not write O at the end. Right? So bis cyclopentadienyl. Then what is left? Iron oxidation number. Any questions are in this? Respond. Do you have any questions in this?
No, sir.
In one case, I will give name. You try to give formula, right? Tris ethylene diamine. Tris ethylene diamine. Chromium 3 chloride. Chromium 3 sulfate. And give the formula. And give the formula of it. Ethylene diamine symbol is En. While you are writing symbols also, we need to follow alphabetical order, sir. Right? In case of En, E should be taken as alphabetical order while you are writing formula, right? So En3, chromium means Cr, En thrice, close the brackets, sulfate, over. What is the oxidation state of chromium? So coordination sphere charge is +3, sulfate 2 minus. So I have to write 2, 3. What I told? While you are balancing the charge, we don't represent that 2 times or 3 times of that complex. Is it clear? Response, sir. Any questions are up to here? Respond. Do you have any questions? So this is about IUPAC nomenclature of coordination compounds. Right? So once open your target booklets. See this? Addition compounds, this topic is over. Coordination entity, central atom, ligands, coordination number, coordination polyhedron, oxidation number, homoleptic, heteroleptic, hard and soft acid base principle, classification of ligands, anionic ligands, neutral, cationic, based upon denticity, monodentate, bidentate, polydentate, ambidentate. Ambidentate also have we discussed or not? Ambidentate ligands means any one of the ligand atoms are donors. Flexidentate, sigma donors, right? Sigma donor, pi acceptors, pi donors. Respond. Now they have given list of ligands, names of few ligands, and this list they have given. Then IUPAC nomenclature of ligands means complexes. This part also over, right? They have given to write formula from name. They gave some rules. Then name to means formula to name. So both we combined and we written them as a single, right? We kept all those rules in same list. Then they have given some examples. Now see this exercise. Which of the following is not an ambidentate ligand? Which is not an ambidentate
Sir, option
ligand?
4.
NH3.
NH.
In order to confuse you, they might have given carbon monoxide here. Then it is good. Right? Carbon monoxide is also monodentate ligand. In carbon monoxide, which is donor? Always carbon is donor. Yes or no? Carbon monoxide, carbon have lone pair, oxygen also having lone pair, but always which will donate electrons? Carbon only. Right? It is not ambidentate, it is monodentate only. Right? Now, what is the IUPAC name of this complex? Hexa double M. Double M.
L2.
Hexa amine cobalt 3 chloride. Correct? Here they gave no, not only space, amino they gave. Correct? Neutral molecule, na? We have to name it as amine. Next, this we have already seen. Potassium, hexa, cyanido, ferrate 2. Correct? Oh, just now we have seen.
Option 4, sir.
Tris, ethylene diamine, chromium 3 sulfate. Fourth option.
Option 4.
Right. Next. Isomerism in coordination spheres, right? So first let me complete that isomerism part and I will come back. If you complete isomerism, sir, more than 70%, 80% of this chapter is over, right? Isomerism of complexes. Very easy topic. Isomerism. And what are the conditions for isomerism, sir? Same molecular formula, but differ in their structure or three-dimensional arrangement, correct? Differ in their arrangement of ligands, either three-dimensionally or through bonding. We call them as isomers. This isomerism is classified into two types, like organic chemistry: structural isomerism and stereoisomerism. Right? Now, first I will start with structural isomerism. Structural isomerism. Directly, I am starting giving examples, sir, instead of writing all those rules, right? So I will explain along with examples. First type of isomerism, ionization isomerism. Sir, good morning, sir. Sir, yes, sir. He has not opened that shutter. That's why he parked it there. And the key is there below on this side. Yes, sir. Yes, sir. Yes, sir. Yes, sir. He is with the physics, sir. Kalyan Sundar, sir. Ionization isomerism. Here, sir, see how much rowdyism is there in Madurai. We are paying rent, right? But we need to follow the rules of security guard. He will come to office at 9 o'clock. Till then, shutter will not be open. Our classes are from 8:30. That is building security guard, not Akash security guard. He will come only at 8:30. And he will leave, sorry, by 9 o'clock. And he will leave office by 9 o'clock. Even if you have any urgent work, You need to leave the office by 9 o'clock. Otherwise, he will lock and shutter. He will close the shutter in spite of anyone inside. Just close it and lock it. Old man. If you say anything now, he will come for a fight. Even if you raise it, your hand, we will become criminals. Very old person now he is. We cannot say anything, but he will use all bad, foul language and anything. Huh? Really, I hate this place. Not only my opinion on total Madurai is gone. No one followed traffic rules. Drainage system is worst. Right? Everyone comes for a fight. Literally, I have wasted money on my car because of these idiots in this city. Literally, I might have spent more than another car cost. They will never follow any rule. Again, in my class only, yeah. Right. Right, sir. Ionization isomerism. Conditions. Again, same. Same molecular formula. Second condition. Differ in, see the conditions, sir. Differ in ligands. I can't call it as ligands. Reason, if it is present inside coordination sphere, I have to call it as ligand. If it is present outside, ion. So these two, if I exchange, right, then it is ionization isomerism. So differ in their ligands, or I will write ions, right? Or I will do one thing, differ in their ions produced during ionization. By dissolving them in a suitable solvent. By dissolving the complex in a suitable solvent, we will see type of ions generated. If they differ in their ions, but having same formula, then they are called as ionization isomers. For example, say this. Chromium, NaH3 5 times. NaH3 I'm taking, if I take 5 number of, then SO4 2 minus, okay, monodentate. So I will take 5 times SO4 bromine. Then what is coordination sphere of central atom? What is coordination number of central atom? 6. Are 5 ammonia molecules, 1 sulfate ion. Now I am exchanging these two. Chromium, NaH3 5 times, bromine, SO4. Now, if I dissolve this in water, what are the ions generated? It will produce Br minus ions, whereas this will produce SO4 2 minus ions. So both have same molecular formula, but differ in their ions. So this will furnish sulfate ions, whereas this will furnish bromide ions. That's why we call them as ionization isomers. Any questions in this online? Do you have any questions in
sir.
this?
No, sir.
Next, linkage isomerism. Linkage isomerism. Generally, linkage isomerism is shown by ambidentate ligands. Complexes with ambidentate ligands generally show linkage isomerism, right? They have same molecular formula, but differ in linkage of ligand towards central atom. Right? Now see this example. Chromium. I have taken already chromium complex. Cobalt, same example given in your target booklet. NH3 5 times, NO2, Cl2. Cobalt, NH3 5 times, ONO, Cl2. Observe the difference, sir. This is red color complex, this is yellow color complex. Give the name of this complex. Give the name of the first complex, sir. Pentaamine, nitrito, N92. Pentaamine, nitrito, N, cobalt 3 chloride. Next one, pentaamine, nitrito, O, cobalt 3 chloride. So nitrite is ambidentate ligand and hence it can show linkage isomerism. Observe if the linkage site changes, means if a ligand changes, complex properties also changing or not. Its color also changing, right? Next, sir. Third type. Coordination isomerism. Coordination isomerism. This is generally shown by polynuclear complexes. What do you mean by polynuclear complexes? More than one central atom. So polynuclear complexes. Same molecular formula. But differ in their ligands coordinated to central atom. Means there will be exchange of ligands. There will be exchange of ligands between cationic part of coordination sphere and anionic part of coordination sphere. There is exchange of ligands between cationic part of coordination sphere and anionic part of coordination sphere. For example, chromium, NH3 6 times, cobalt 6 cyanides. Now observe this. What is the oxidation number of central atom in first coordination sphere? Can write +3. Then overall charge will be +3. Now here overall charge is -3. Here cobalt also +3. Acceptable or sir? Respond. Now what I'm doing, I am exchanging these two. Right? Either one ligand or two ligands or all the ligands, whatever you want, you can do it. So I am changing all the ligands. When I change all the ligands, I will write CO here. Why? Why, sir? I am writing cobalt here. Cationic part. The moment if I exchange all, 6 cyanides comes here means overall charge of this coordination sphere becomes positive. That's why I'm writing it first. Chromium, Cn 6 times. Both have same molecular formula, but differ in ligands which is connected to central atom. Here ammonia connected to chromium, there ammonia connected to cobalt. Cyanides connected to cobalt, here ammonia connected to cobalt. Cyanides connected to chromium, right? So these two are examples of coordination isomerism. Next, solvation isomerism. Any questions, sir, in coordination isomerism? Online, someone respond. Do you have any questions in it?
No, sir.
No, sir.
No, sir.
No. Regarding solvation, do you want to give nomenclature of this one? Give name of this one, either top one or second one. Name of it. Hexa, amine, chromium 3, hexa, cyanido, cobaltate 3. Cobaltate 3. Next one. Hexa, amine, cobalt 3, hexa, cyanido, chromate 3. Clear? Now coming to this one, solvation isomerism. Same molecular formula, differ in number of solvent ions inside and outside coordination sphere. Same molecular formula, differ in number of solvation molecules or solvent molecules inside and outside coordination sphere. Right? If they are present inside coordination sphere, what we call them as ligands. If they are present outside coordination sphere, we call them as solvated, hydrated. Correct or not? Or inside coordination sphere, same water molecules is called as aqua. If same water molecule is present outside coordination sphere, we are writing it as hydra. Correct or not? Hydrate. Respond. So inside means I will call it as coordinated. Outside coordination sphere means I will call it as solvated. Right? For example, I'm taking examples. Chromium, H2O 6 times, Cl3. Chromium, H2O 5 times, chlorine. Chlorine, Cl2 dot H2. This is a violet color complex. This is a gray-green colored complex. Give the names, sir. First one, give the name of the first complex. Hexa-aqua. Hexa-aqua, chromium 3 chloride. Second one, penta-aqua, chlorido, chromium 3 chloride hydrate. Correct? Next type of isomerism, coordination position isomerism. coordination, position, isomerism. Same conditions, same molecular formula. Differ in ligands and their position. Generally, it is observed in bridged complexes or bridged ligands. Complexes with bridged ligands. Generally observed in complexes with bridged ligands. Right? For example, say this. I'm taking tetraamine cobalt. Here I am taking OH and chloro. Again, I am taking cobalt, NH3 twice Cl2, SO4. If I take here 4 ammonia molecules, here instead of cobalt, if I take another complex, another metal atom, chromium, then it also comes under another class of isomerism. Coordination isomerism. Are you able to understand? And if both central atoms are different, then it is polynuclear complex or not, right? Then it comes under coordination isomerism also. Now both central atoms are same, right? It is also polynuclear, but both central atoms are same, right? Now I call it as coordination position, because here ammonia connected to cobalt only, chlorine also connected to cobalt. Even if I exchange ligands, then also all ligands are connected to central atom, same cobalt central atom, but their positions are changing. That's why it is called coordination position isomerism. Is it clear? Observe the difference again. One more time. Observe this one. Coordination isomerism. Coordination isomerism means central metal atoms are different. If I exchange ligands, position is changing, right? And also to which metal atom they are coordinating, that also changing. Correct? Response, sir. That's why we call it as coordination isomerism. Here, central atom ligands connected to same central atom, whether I exchange them or not, right? Ligands, all ligands are connected to same central atom. Only position is changing, not coordination. Clear? That's why it is called coordination position isomerism. Can you give IUPAC nomenclature of this complex? Give IUPAC name of this complex. Tetra, amine. First identify oxidation state of cobalt. Here 2 minus means can write +2 here, right? So overall +2. 4 ammonia molecules means 0. So 4 into 0. 2 cobalt. So I'm writing +2x. OH is -1. Chlorine is also -1. So -2. Again 2 ammonias 0. Again -2. Overall equal to +2. And then what you got? 6, huh? So 3 means +3 here, +3 here. Acceptable or not? So name tetraamine cobalt 3 mu HCl. C. So mu chlorido, again mu hydroxido, diamine, dichlorido, cobalt 3 sulfate. Clear? Any questions? Now observe this. I am exchanging one chlorine from here to here. NH3 thrice chlorine, cobalt, OH, Cl, again cobalt, NH3, array. Do N comes first, Cl comes first, man? Which comes first? Cl, NH3 thrice. Here also, cobalt, Cl, NH3 thrice, SO4. Now give the name of it, sir. Now give the name of it. Triamine, chlorido, cobalt 3, mu chlorido, mu hydroxido. Again, triamine, chlorido, cobalt 3, sulfate. Clear? Response on any questions? Respond. Now see this. We are seeing isomerism in which first one? Structural isomerism. In structural isomerism, ionization isomerism, linkage, coordination, solvation, coordination, position. Done. So all these types of isomers are done. Now we are going to stereoisomerism. Stereoisomerism. Already you know that stereoisomerism again classified into different types. Geometrical, optical. Correct? Geometrical isomerism means condition. Planar, restricted rotation. What, sir? Restricted rotation, planar, difference in spatial orientation. If these three conditions are satisfied, geometrical. Right? Now what about optical? If I pass plane polarized light, if you rotate that plane polarized light into either clockwise or anti-clockwise, then it is optical. Or I cannot cut that molecule into two equal halves. If there is no plane of symmetry, then that complex is obviously optically active. Correct or not? Right? So just I will stop now. Go for break. Come back in 10. Already, I think class is up to 10 o'clock. See, I am leaving you 3 minutes early. Right? Come back by 10. Next 2 classes also chemistry only. Today, till I match you with weekday students, I will not leave. Right? Coordination complexes over there. Then alkyl and aryl halides. In that, introduction is over. Physical properties also over. Preparations. In weekday classes, what I am doing is not I am following preparation methods of your target booklet. So already we discussed last year what I told you. Preparing alkyl halides from all means from alkanes, from alkenes, from alkynes, from alcohols, from aldehydes, ketones, carboxylic acids, amines. How to convert every functional group to alkyl halides. So we will discuss that first so that it will give one revision of hydrocarbons chapter also. After that, in chemical properties, I will discuss how to convert alkyl halides to alkanes, alkenes, alcohols, aldehydes, ketones, carboxylic acids, amines. Means converting every functional group to alkyl halide in preparations. In properties, converting alkyl halides to every functional group in chemical properties. Right? If you read one chapter perfectly in that, remaining all chapters 50% is over. Right? Indirectly, class 11th hydrocarbons revision also will be over. Right? So at least listen to alkyl and aryl halides chapter very clearly, seriously. Right? If you are done with that, next chapter alcohols and phenols ethers, 50% chapter will be already over. Just I will write the reactions only. Same way, next chapter, aldehydes and ketones also same. Only special reactions, neighborhood reactions, those cases I will explain in detail. In remaining cases, just I will give the reactions, right? So alkyl and aryl halides, I will take more time. Let us complete it in detail. Right, sir? Go for break. Join in the next link, sir. Online students.
Thank you, sir.
Thank you, sir.